Hi, my name is Diego Esquivel, and today I will be presenting a survey of quick security and privacy vulnerabilities based on Hoarder and Fung's Exploring Quick Security and Privacy, a comprehensive survey on quick security and privacy vulnerabilities, threats, attacks, and future research directions. In this presentation, you can expect to hear a mid-level detailed, high-level overview of the QUIC protocol. The QUIC protocol was created by an internal team in Google in 2012 and was originally called GQuick or Google Quick. This protocol was built with the intention to provide reduced latency, improved congestion control, connection migration, and encryption by default. From 2012 to 2021, the good folks in Google collaborated with many people and organizations, including the Internet Engineering Task Force, to produce a protocol that did just that. And in 2021, the Internet Engineering Task Force recognized QUIC as RFC 9000. In 2022, HTTP 3 was released as RFC 9114 and officially utilized QUIC as its transport layer protocol. In 2023, QUIC version 2 was released as RFC 9369. All discussion about QUIC and its security and vulnerabilities are done within the context of HTTP 3. And this diagram here shows what the HTTP 3 protocol stack looks like next to its predecessors HTTP 2 and HTTP 1.1. HTTP 3 is drastically different from its predecessors, as shown in this diagram, but it still provides many of the same services that its immediate predecessor, HTTP 2, provides. It provides these services in a different way. In addition to this, I will also tackle a knowledge gap in security and privacy challenges of the QUIC protocol, which is common to many new QUIC adopters. Finally, I will briefly mention directions for future research to reduce the vulnerability surface of the QUIC protocol. When I first heard of the QUIC protocol, I thought it was amazing, but I questioned how it could possibly provide reduced latency, improved congestion control, connection migration, and encryption by default for HTTP 3, and how it could do this better than HTTP 2, because HTTP 2 was already great at this. The truth eventually became clear. HTTP 3 does everything HTTP 2 does with help, only better. The diagram teetering here is HTTP 3. QUIC enables HTTP data transfer by connecting a web browser to the internet through a quick connection. And this quick connection uses numerous mechanisms to provide stream multiplexing, congestion control, loss recovery, error correction, forward error correction, actually, connection migration, security, flow control, version negotiation, and minimum transmission unit discovery. After accepting HTTP 3 as superior to its predecessors, I wanted to know what its packet looked like. This is what the HTTP 3 packet looks like. HTTP 3 uses QUIC and QUIC uses UDP. The order of those clauses is extremely important. An easier way to an easier to follow way to say HTTP 3 would be HTTP over QUIC over UDP. And this diagram here does a great job at showing how the protocol packets in HTTP 3 get stacked together. The fact that QUIC is UDP based is where our first class for vulnerabilities comes from. The use of UDP gives the QUIC protocol vulnerabilities to, and challenges defending, amplification-based attacks, which ultimately result in resource exhaustion, denial of service, and exploitation of the connection migration and zero round-trip resumption services. Examples of amplification-based attacks are flood DDoS, UDP hole punching, and slow LoRa's. Next, the actual QUIC part of the packet sits in the payload of the UDP packet. The QUIC header contains flags, a connection ID, and a packet number. This is followed by the QUIC payload, which is made up of a frame ag field, a frame control field, a header for the stream frame, and the stream frame payload, which in this context is filled with HTTP data. The QUIC packet is finished with a QUIC MAC code. Most of the fields in the QUIC packet are encrypted by default, and this is where the next class of vulnerabilities comes from. If the encryption algorithm, the key exchange method, key management, implementation, or storage of secret information is weak, then encryptions can easily be undone by an attacker with enough compute power. This vulnerability leads to congestion control manipulation, which causes denial of service or service quality degradation through attacks such as drown, decryption, and side channel. Additionally, the fields that are unencrypted enable another class of vulnerabilities. The unencrypted data, besides for the MAC code, are required for routing operations and introduce the risk of data leakage. In addition, this data, the unencrypted data, is not protected against manipulation. Attackers can use man-in-the-middle based attacks to determine what data is being sent by analyzing traffic, patterns, and endpoints, which leads to the compromise of the data confidentiality. Additionally, attackers can use leaked data to impersonate other hosts in impersonation, selfie, and forgery-based attacks. Attackers can also change the unencrypted data to set different encryption keys and connection IDs. In attacks to cause resource exhaustion, connections to delay by forcing a version negotiation, or even completely hijacking connections, compromising the data's confidentiality, integrity, and availability. Attacks which take advantage of these ideas include server configuration reply, version, version forgery, quick reset, and source address token tampering or manipulation. It's obvious now that QUIC has many vulnerabilities. After realizing this as a newcomer to QUIC, I still wondered how this could possibly be better than HTTP2. Here is what the normal HTTP2 packet looks like when compared to HTTP3. It's obvious that HTTP3's security is on a stricter level than HTTP2's security. These two versions of HTTP still have vulnerabilities though, but HTTP3 encrypts much more data than HTTP2. After learning what an HTTP3 packet looks like and the way it compares to an HTTP2 packet, I wanted to learn what starting a connection looked like and how it compared to starting an HTTP2 connection. This diagram shows what a normal start to an HTTP session looks like across both versions. Before TLS 1.3 was released, HTTP2 could be secured through the use of TLS 1.2. TLS 1.2 required 2 round trips to establish security. This meant that in HTTP2, you could not start sending HTTP data for 3 round trips. 1 round trip was required to set up the TCP connection, depicted by the orange arrows, 2 round trips to establish the security, depicted by the black arrows, and then HTTP data can be sent securely. When TLS 1.3 was released, one notable improvement was the reduction of 1 round trip to establish security. Now, HTTP data could be sent after only 2 round trips in HTTP2. 1 round trip was required to set up the TCP connection and 1 round trip to establish the security. In HTTP3, setting up a quick connection and security, depicted by the blue and black arrows, can be done in one round trip. This enables HTTP data to be sent after only one round trip. It's obvious now that HTTP 3 is faster than HTTP 2, but this does not mean it is more secure. The setup phase for a quick connection is vulnerable to many of the attacks previously mentioned, and this phase is where flood, DDoS, forgery, configuration, tampering, and slow LoRa's-based attacks happen. An additional feature of QUIC is not a QUIC exclusive feature, but instead is a feature of TLS 1.3. This feature is zero round trip session resumption. This is something offered by both HTTP 2 and HTTP 3. However, it looks very different in both versions. In HTTP 2, one round trip is required always to establish the TCP connection, and on the next round trip, the security can be set up and HTTP data can be sent as well. In HTTP 3, the connection and security can be established in the first round trip, and data can also be sent in the first round trip. Although zero round trip service resumption is very desirable, it is also where many attacks take place, such as reset, negotiation, implementation, and information leak-based attacks. When the good folks in Google were working on QUIC, they needed to make an assumption about the security. This assumption led to the following statement. The effectiveness of QUIC security mechanisms relies on the strength of the underlying cryptographic algorithms for encryption, key exchange, and authentication. This statement means that if any of the pieces are weak, then the security QUIC provides will also be weak. This makes it obvious that a lot of care must be taken when implementing and setting up QUIC for your network applications. The assumption the good folks made was that endpoints are to be considered secure against compromise, and this assumption led to the good folks focusing the security guarantees of QUIC to only the transport layer. Thanks to this assumption, QUIC was able to make many improvements over its predecessors, such as faster zero-RTT resumption and increased encryption, but it is still weak to many well-known attacks, such as flooding, impersonation, and man-in-the-middle based attacks. With the rise of AI came AI-generated attacks. AI-generated attacks take advantage of human errors that occur during the implementation and setup phase to compromise systems. AI-generated threats usually are partnered with phishing and social engineering-based attacks to compromise systems. Additionally, passive attacks are still mostly undetectable by most systems, and the dependence on TLS 1.3 makes the protocol vulnerable to quantum threats. Research aiming to improve the security of QUIC happens in developing stronger, quantum-safe foundational encryption algorithms, creating a diverse environment of QUIC implementations and support libraries, compromising speed for security, padding packets, reshaping traffic, creating advanced firewall configurations, which are often customized for a client, and deep traffic and packet analysis to uncover malicious activities. A couple of recent technologies are encrypted client hello, ECH, which uses pre-shared keys to encrypt the setup phase to provide increased resilience to forgery and handshake-based attacks, and private relay solutions, which use private proxies to hide client IP addresses and traffic activity to protect against analysis and impersonation-based attacks. Much more research is needed to develop and build DDoS resilience and quantum-safe algorithms, and protect against website fingerprinting, among a number of other threat surfaces. These are my works cited.